Hi students, welcome to HSC Earth and Environmental Science and Module 6 on hazards. This is our penultimate video, number 21. We're going to look at technology, disasters and human society. In this video, we are going to specifically address the learning intention to investigate and evaluate the technologies used to minimize the effect of natural disasters associated with volcanoes and earthquakes, including building codes, disaster warning systems, and education. So we want you to be able to identify some of the important technologies and early warning systems, the strategies that we use to try and minimize damage, including things like public education and evacuation programs, and also to evaluate how early we can get information and how effective that information can be when we roll it out. So what we're trying to do now is we're trying to minimize hazards. And in order to do that, we want to specifically apply these strategies to volcanic eruptions and also to earthquakes. So when we're talking about volcanoes, what we really are talking about is trying to be able to predict a volcanic eruption, perhaps the type of volcanic eruption, whether it's likely to be effusive or explosive, and what sort of people or property are going to be in danger from that. Now, we've talked about the fact that one of the things associated with imminent eruptions is some classic changes that might be occurring in the topography in particular that may be indicators that something is about to happen. We talked about this in a previous video, so we're looking at changes in the shape of the volcano, in the heat signature, in any bulges, ground level changes, changes in the groundwater chemistry, which maybe suggests that certain types of gases, for example, might be coming out of the volcano, already leaching through some of those cracks and maybe are getting into the groundwater. And of course, gas from certain types of features associated with volcanic eruptions like fumaroles are all ways of trying to get a little bit of an idea ahead of time when an eruption might occur. Now, this might be anything up to, say, days before an eruption. And obviously, if we've got days, we've got a little bit of time to work with here. So we can perhaps organize some sort of an evacuation program, some way of trying to get people away from the site of the problem. But as we've mentioned previously, what we can do is get an idea that something's going to happen. We may not necessarily be able to predict with accuracy that this volcano is going to blow tomorrow afternoon at 4:38 p.m. This is something that we just can't do in terms of our volcanology at this point in time. So the exact predictability of an eruption remains a little bit of a mystery at this stage. Of course, the problem with earthquakes is we're not talking about days now. Sometimes we're talking about minutes or even less. So once we start to recognize what's going on with picking up some of those P waves initially from a potential eruption earthquake event, then we have a very small window of opportunity to try and get people out. Usually there's not sufficient time to get people out. So what can we do? Well, we can just try and work in some of the ways of trying to minimize the damage as much as possible. So minimizing damage from earthquakes is often what we do before the fact, not what we do during the fact. There are a couple of strategies which we will look at, but really the idea about reducing damage from earthquakes is concentrated in the engineering solutions associated with buildings and also in education programs that allow people to know what to do and how quickly to get themselves into at least as safe a position as they possibly can. You would expect places like the west coast of the US and Japan to be leading the world in some of the earthquake engineering and education programs that they've developed specifically to try and deal with their higher than average incidence of earthquakes. And of course, in the case of Japan, volcanic eruptions as well. So this is really a very tectonically active region. They've had to deal with a huge amount of these potential disasters. So they have, by necessity, but also by a lot of skill and preparation, produce some very, very good strategies that are very effective in trying to at least minimize the damage associated with these sorts of events. Prevention is obviously one of those things that we have problem doing. We can't really prevent volcanoes from erupting or earthquakes from shaking the ground, but we can try and put things in place. Certainly, one of the things we'll look at the end of this video is the difference that it can make by having certain strategies, certain codes in place, certain practices where the public knows what is expected of them, and countries where maybe this is not the case. So we need to look at 3 areas specifically to try and get a bit of a picture of what's going on with each of these. So I've set up tables again. I think tables are a really nice way for you to organize your information. This time giving us a bit of a description and an example that we can walk through for each of these 3 areas. So the first one we want to look at is building codes. And building codes are mandated by government departments. So they could be local government or regional government departments. They might be state, they might be federal level governments, departments that are setting certain standards. In Australia, we call them the Australian standards. And they did change, particularly in Australia, as a result of the Newcastle earthquake, which was, I think, in about 1989, somewhere around there. And that caused a huge amount of damage, and obviously it promoted the idea of developing building codes that were going to protect some of these buildings a little bit better from any future shakes. As we talked about with a previous slide, the frequency and the severity of the disasters are more likely to have an influence on what sort of strategies are put in place. So these sorts of things might be characteristic of buildings that are in areas where they are more likely to be prone to earthquake damage. So isolating the base and creating some sort of force damping. Think of it as I guess, a suspension system for a building that's able to sort of rock and roll on its own and take some of that stress and that strain before it gets translated through to the other parts of the building. Structural reinforcement and flexible materials that are able to bend and sway. One of the problems that buildings have is that they're very good at vertical forces. So obviously, there's got a lot of weight sitting above, particularly multiple story buildings. So being able to cope with the weight that's coming straight down is usually something that most buildings, often designed to do. It's the sideways shaking that you get through an earthquake that it can create problems. A lot of engineers have recognized this idea of building resonance. So this is the kind of idea that, if you have a group of people that are all walking across a bridge and they're all walking in sync, marching, and that what can happen is the bridge can start to shake as a result of the resonant frequency linked by all of those marching feet. Same sort of thing if an opera singer hits a high note and makes a glass vibrate sufficiently in order for it to smash. So at these frequencies, now this doesn't happen all the time, but at a particular frequency, it's more likely to create this additional damage. The same sort of thing can happen with buildings. If the earthquake vibration kind of corresponds to the building's resonant frequency, it can shake so much more, and like glasses or like bridges, the damage can be much greater. So one of the solutions was to try and contain resonant frequencies to different floors, change the way that the building was constructed so that maybe if one floor was going to correspond to the resonant frequency of the earthquake, that other floors above it or below it would not. So in that way, trying to minimize things. An example of that's the 1970 development of the Trans-American Pyramid in San Francisco. Disaster warning systems are also something that is used to try and minimize damage from these sorts of hazards, volcanic eruptions and earthquakes. Again, some of this is dependent on how much notice we're able to give associated with each of these different types of disasters. But again, it's usually government agencies that have these sorts of early warning systems. We know in Australia, we've got some very important emergency services, and they're going to obviously be at the forefront of any of these sorts of early warning systems because they're often also going to be our first responders. So when hazards are detected, automatic alerts can be sent out. This can happen via radio, via mobile phones, through texts, for example, other electronic devices, and often through news services. With the computer technological age that we have, we've got so many different ways of connecting in with all sorts of different providers, and these are being taken advantage of when we're looking at these systems. Again, it doesn't surprise us that Japan and the US are places where we have specific types of alert systems that have been developed over some time. The J alert system in Japan and the Shake alert system for the United States. Part of the problem with these systems is that if you're going to try and automate them, which means you don't have people having to make decisions in real time, you just automate them, sometimes little things can happen that can trick the system. In 2018, two minor earthquakes occurred concurrently, so almost at exactly the same time, which tricked the system into thinking there was a bigger earthquake than what there actually was coming. And so, again, these warnings were sent out prematurely, and in that case, certainly no major damage was done. A reverse problem, I guess, occurred for the Shake alert system for Los Angeles residents when a 6.4 magnitude earthquake hit them in 2019. Now, the system had been set up for anything above a magnitude 5 to set out an alert, but this epicenter was about 200 kilometers away, and so therefore it wasn't deemed to be sufficient magnitude to send out an alert. And of course, the people in LA were a little bit miffed about that. So a lot of discussion occurs around these early warning systems, particularly where they need to be automated, because when they are automated, then we need to have some sort of levels set in them so that something, once it triggers, will then be pushed through. Now, hazard warning systems are great, but if you don't have an educated public, if the public don't know when they get these warnings, when they see these sorts of things on the news services or they hear them on the radio, what they're supposed to do, then the warning systems themselves are not going to be of much value. As we talked about, volcanic eruptions can sometimes give us a little bit of time to organise some sort of an evacuation of the people from an area. But the problem with earthquakes is they happen too quickly. Often we just can't evacuate people. So what we can do is we can look at some ways of trying to minimise things. Open lifts, for example, get people into places where they're out in the open, away from areas that could be collapsing in on top of them, making sure that we've thought about our systems of water piping, for example, electrical systems. So often those thinking about the grids that would run around, above or below each of the cities, that very important in keeping sewage, in keeping water, in keeping communications, electrical systems going, that we think about ensuring that we've made some adjustments to avoid overloading those systems or breakdown in those systems. A lot of the time with earthquakes, it's not just the initial earthquake going through that does all the damage. It's some of the other things that happen as a consequence. And remember, when we're looking at hazards, we're also looking at recovery time. So it's not just what the damage is at the time, it's also how long it takes to get everyone back to normal, in inverted commas. Japan continues to be one of the leaders in this sort of an area, and you would probably expect a Japanese system to be very strong in its education programs, and in fact they are. They run specific days through the year for preparedness programs. There's programs that are taught to school-age children. They carry out mock drills. They get taught life-saving techniques, and also they have training in evacuation techniques so they know what, when, and how to evacuate when these different types of early warning systems are put in place. And when you consider the number of damaging earthquakes that are felt in Japan each year, you'd have to give these Japanese programs some serious ticks in the area of effectiveness. So that just leaves us with something to have a little bit of a think about in terms of comparison. In 2010, a magnitude 7 earthquake hit the island of Haiti. This created somewhere, depending on what records you look at, between 200 and 300,000 lives lost and a similar number of people who were either injured or displaced. A larger earthquake hit the following year, 2011, in Japan, a magnitude 9, and it was also accompanied by a tsunami. yet the number of lives lost was closer to about 21,000. Now, this is kind of a good little case study for us to think about in terms of hazard minimization, in terms of technologies that are being applied in different situations, in terms of the culture, the society, the general wealth and education that's being afforded to the population in each of these two different areas. So what we're going to have a look at is just a little case study example of how similar sorts of disasters or disastrous events happened in these two different places, and yet the outcomes were so significantly different. But that's something to have a look at in class. Thanks for watching.